Alright, so in this video I am going to show you the capacitance of two special capacitors. So a capacitor doesn't have to be parallel plates. The simplest one is this: one plate, another plate, and you put charge plus plus, for example, minus minus. This is the simplest device you can have to store energy and charge. And so the capacitance for this simple device will be epsilon 0, the area of the one plate over the separation D. This is the simplest one. Now we can also have this kind of geometry: concentric cylinder, one cylinder with radius A, and outside another cylinder with radius B. And so here, if I charge this inner surface plus plus plus, the red, so by influence I will have the other side minus minus minus. So it's like having two plates against each other, plus and minus. So we have created a capacitor. The question is, how much? What's the capacitance of this kind of capacitor? So the steps are these: one, find E using Gauss. Gauss, much easier. Two, find the voltage through the equation. Alright, I'm going to write here the voltage V between A and B. So VB minus VA is minus the integral from A to B E dr. So first step, find E using Gauss. Once you find E, put it here and use the definition of differential potential between 2 points in space to find the voltage between 2 points, in this case A and B. The next step is to evaluate C, which is equal to Q over V. That's strategy. Okay, find E, find the voltage, find C. Let's apply this to cylinders. So the field E using Gauss law, 2 pi r L, this is the lateral surface, the base will have no contribution to the flux, and we did this several times in class. So this is the field due to this Gaussian surface in green. The only charge enclosed is the red one. So that's it. Now what is the voltage between A and B, the inner and outer radii of this cylinder? So the integral from B to A with minus. Notice I'm going from B, the lower end, to higher end, which is B plus EDR. And the integral will give you this quantity, Q over 2 pi epsilon 0 L natural log B over A. So these are the steps: find E, find V. Now the definition of C is the charge over the voltage, Q over V, and Q is just Q, and this is V. Reduce everything, and this is the capacitance. So it's 2 pi epsilon 0 L over natural log B over A. Notice again, the capacitance is not function of the voltage of the charge, it is function of the geometry, the length and radii. Let's apply the same thing to two concentric spheres. This one of radius A and here radius B. So the strategy is the same: find the field using Gauss law, then evaluate the voltage, then divide the charge by V. So I'm going to choose a Gaussian surface, that is sphere, the green, that includes this positive charge in red. According to Gauss law, I'm going to find E equals the charge. So I will have the charge divided by 4 pi epsilon 0 r square. We did this several times in class. Now let's evaluate the voltage. Now the voltage V, again I'm going to start from B to A. Why? Because I'm going from low to high, so equals minus A to B. The lower end is yes, B. Okay, yes, I start from, yes, okay, so this is EDR. Alright, is this correct? I'm going from B to A. Now this is wrong. This is wrong. It doesn't really affect the outcome, but the sign, we'll have problem with the sign. We don't want to have negative quantities. So let's try again. So I'm going from B to A, so that's VA. So VA minus VB. Okay, we start from B. This is minus the integral from B to A EDR. This is right. Alright, so I'm going to call this just V, the difference potential, which is equal to minus, I put everything outside, Q over 4 pi epsilon 0, and that's it. So the integral from B to A, now I'm left with dr over r squared. So the V is just Q over 4 pi epsilon 0, and this is clearly minus 1 over r, the integral of r squared, evaluate between B and A, which is equal to the negative sign is still here. Alright, so this is Q or minus Q over 4 pi epsilon 0, and this is just so minus 1 over A minus 1 over B. Now this is just so this is minus Q over 4 pi epsilon 0, and then I have minus 1 over A plus 1 over B. Now I can put this minus inside and change, so the voltage V is Q over 4 pi epsilon 0, and then I have 1 over A minus 1 over B. Can you see the minus become plus and the plus becomes minus? Now I can reduce the same denominator, so V equals Q over 4 pi epsilon 0, and this is B minus A over AB. You see, the idea is to have B minus A some positive quantity. Alright, so now C is equal to the charge, the total charge over the voltage between the plates, so which is equal to Q divided by Q over 4 pi epsilon 0, and then you have B minus A over AB. Now we can rearrange this equation and find Q. Well, I lose Q on both sides. I don't have to deal with the Q again, so there is no Q. So the answer will be 4 pi. I'm going to write here C is 4 pi epsilon 0, and then AB upstairs, and I'm left downstairs B minus A. So let's put it here. C, the capacitance of these concentric spheres is 4 pi epsilon 0 A B over B minus A. And there you go. Again, the radius is enough to define a sphere, so it is basically the geometry of the sphere, and therefore the C, the capacitance, again is its function of the geometry of the capacitor. It's not function of the voltage or the charge. Similar to this one here, it is function of L and then radii. So this video shows you that the capacitance can be, it's always functional geometry, but it can be complicated, logarithmic or polynomial. So it doesn't have to be very simple like this, which is for two plates. It's very simple. It's the area divided by the separation.